Look at our world from space, and you see a brilliant blue marble, shimmering with vast oceans. For centuries we thought that all of Earth's water was right there on the surface. Oceans, lakes, rivers we know so well. We calculated that if you gathered all this water into a single sphere, it would be about 860 miles wide. But what if I told you our planet might be hiding a reservoir so immense it could fill our surface oceans not just once, but perhaps 3 times over? This isn't science fiction, it's shaking the very foundations of geology and our understanding of the planet we call home. This hidden water isn't a liquid ocean you could sail a submarine through. It's far more subtle and more profound. Imagine a colossal, saturated sponge made of rock, under immense pressure and searing heat, hundreds of miles beneath our feet, in the mantle. The discovery that so much water could be locked away deep within Earth is a revelation, forcing us to redraw our mental map and add an unseen layer to its complex systems. It's a journey from the deepest mines to advanced laboratories, from the violent shudder of an earthquake to the quiet analysis of a tiny diamond. Patient science peeled back Earth's layers, revealing a world more active, complex, and watery than we imagined. We live on a water world, in more ways than one. So, what exactly did scientists find? An enormous zone of water-rich rock deep within Earth's mantle. This region, known as the transition zone, sits about 410 to 660 kilometers below the surface. Here conditions are extreme. Pressures over 200,000 times surface levels. Temperatures soaring above 1500 C. This isn't a giant subterranean sea. You wouldn't see a liquid ocean down there. Instead, water is chemically bound inside the crystal structure of minerals, like a sugar cube, absorbing a drop of water. A high-pressure mineral called ringwoodite acts like this sugar cube on a planetary scale. Seismic data and lab experiments suggested the transition zone could hold an incredible volume of water. Some models equal it to all Earth's oceans, others suggest up to 3 times the surface oceans. Surface water is just the tip of the iceberg. Earth is an integrated system with a vast, slow-moving deep water cycle. We know the surface cycle: evaporation, condensation, precipitation. Now consider a deep Earth water cycle working over millions of years, pulling water down and releasing it back to the surface. It's a radical new way to think about how Earth works. How could we possibly see something buried 400 miles deep inside solid rock? We can't drill that far. Our deepest boreholes barely scratch the crust. Scientists became planetary detectives, using indirect clues to picture this unseen world. Seismology was the key. Earthquakes send waves rippling through the planet, like a planetary ultrasound, like tapping a wall to find a stud, hollow sound versus dull thud. Waves change as they pass through different materials. At the transition zone, scientists noticed waves slowing in ways temperature or pressure alone couldn't explain. In the lab, diamond anvil cells recreated mantle pressures and heated tiny mineral samples, especially ringwoodite. Water-bearing ringwoodite slowed seismic waves, exactly like the earthquake data showed. Then came a flawed diamond from Brazil, holding a microscopic ringwoodite inclusion from the transition zone. Analysis showed about 1.5% water by weight, the first direct evidence of water in the transition zone. Seismic maps, lab results, and that diamond all told the same story. The deep Earth holds water. The reaction from scientists was profound astonishment. We long thought water arrived late via comets and asteroids. A massive internal reservoir suggests Earth may have been born wet. This forces a complete reevaluation of the planet's internal plumbing. A true paradigm shift. It's like discovering a hidden bank account that changes the entire balance sheet of the planet. It could influence continental drift, plate tectonics, and even the explosive fury of volcanoes, conduits linking deep earth and surface. At the heart is ringwoodite, a high-pressure form of olivine found only in the transition zone, and in ultra-rare diamond inclusions. Like graphite versus diamond, pressure transforms olivine into ringwoodite. Ringwoodite's crystal structure traps water components as hydroxyl groups, a molecular cage locking water away. Lab tests show ringwoodite can hold up to 2.5% of its weight in water. Imagine every grain of a vast desert is a tiny porous bead. Each holds a little water, but together, the total becomes colossal. The water isn't between grains, it's inside them, distributed across a global layer hundreds of miles thick. Because it's chemically bound, this water can remain for hundreds of millions of years. Earth's deep storage facility. Ringwoodite's water-bearing capacity connected the clues from seismology and geology. A hidden ocean, locked in stone, changes how we see our world. We all learn the water cycle: evaporation, clouds, rain, rivers back to the sea. Now imagine a slow planetary breathing of water, in and out of Earth's interior, over millions of years. At subduction zones, an oceanic plate, saturated with seawater, plunges beneath another, especially around the Ring of Fire. Rising pressure and heat squeeze water from the rock, fueling magma and volcanoes above. Some water is carried even deeper, locked into ringwoodite in the transition zone. The outbreath may ride mantle plumes, hot upwellings that carry water-rich minerals upward. As pressure falls, ringwoodite becomes unstable, releases water, and lowers rock's melting point, creating magma. Over deep time, this cycle could regulate ocean volumes: more subduction, seas fall; more plume release, seas rise. Water softens rock like a wet twig bending more than a dry one, so hydrated mantle flows more easily. This can grease the wheels of plate tectonics. Hot rock rises, cool rock sinks, plates move. Perhaps the secret to Earth's unique tectonic activity is not just surface oceans, but a vast internal reservoir too. Water lowers melting points to feed volcanoes, and its movement in subducting slabs can trigger deep focus earthquakes. Mapping where deep water resides could help us understand powerful, mysterious earthquakes. It all happens in Earth's engine room, the mantle. This discovery reshapes how we search for life beyond Earth. Planets might be water worlds without surface oceans, if their mantles lock away vast amounts of water. Signs of volcanism and tectonic activity on exoplanets could hint at watery interiors. The James Webb Space Telescope can detect gases like water vapor or sulfur dioxide, possible fingerprints of interior water. Mars once had water at the surface. Could some of it be locked deep in its mantle? We have a grainy picture of Earth's watery interior. We need a high-resolution map. How much water's down there? Is it spread evenly, or concentrated in wet spots, steady cycle, or pulses through time? To find out, we'll deploy denser seismometer arrays, hunt rare, deep diamonds, and push high-pressure labs further. We live on a thin crust above a world of profound secrets. The deep Earth is a final frontier, a curious anomaly, a bold hypothesis, and patient multi-field evidence. This is how science builds reality. The water in our bodies, the air we breathe, the ground beneath our feet, all linked to deep forces shaping Earth for billions of years. The clear takeaway: Earth isn't just a water world on its surface. It may be a water world all the way down, and that changes everything. If this blew your mind, subscribe for more deep Earth mysteries and cosmic science.